I used to think the row space was just another space in linear algebra, something I could follow by steps but not really understand deeply. And when it came to the left null space, I wasn't even sure what that meant. But once I started breaking down and visualizing these spaces, things started making a lot more sense. Now take a look at the animation on your screen. The green plane represents the row space of a 3 by 3 matrix, while the red line shows the left null space of that same matrix. This visual will help us dive deeper into what these spaces really mean. Welcome back everyone. So far we have covered the column space and null space. In today's video we will explore two more fundamental spaces, the row space and the left null space. I will guide you through what they are and how to visualize them, helping you truly grasp their significance. So let's jump right in. You say row space. Row space is nothing but the column space. It is the column space of matrix A transpose T. Alright, so row space of matrix A is nothing but the column space of matrix A transpose. That's all. So in the previous videos, we were we used to refer this matrix. We used to refer this matrix, right? 4, 0, 4, 11 and all. So for the same matrix, if matrix A is 0, 4, 11, 0, 4, 5 and 0, 0, 6, then we have already seen what is column space and null space for this matrix. So the row space is nothing. The row space for A is nothing but the column space of A transpose. Basically, you transpose the matrix A and take the column space of it. So what is the transpose of this matrix? It's nothing but 0, 0, 0, 4, 4, 0, 11, 5, 6. That's all, right? So that's all row space is. You can also think it is nothing but the linear combination or span of the rows. Why? Because column space of a matrix is nothing but the span of the column vectors. That is a linear combination, all the linear combination of the column vectors, right? But because in this case A transpose, the column vectors are nothing but the row vectors of the original matrix A. So we can also say that row space is the span of row vectors of matrix, because row space is nothing but the column space of A transpose, and the column vectors of A transpose are nothing but the row vectors of A. So either you can say that row space is column space of A transpose, or you can also say that row space is nothing but the span of row vectors of the matrix. These are row vectors. All right, these are nothing but row vectors. So these are row vectors. Similarly, we have the fourth and last subspace, the left null space. All right. So the left null space is also simple. It is the null space of A transpose. That's all. That's all is left null space. That is left null space NL of any matrix A is nothing but the null space of A transpose. And we already know what is A transpose. It is the matrix 0, 0, 0, 4, 4, 0, 11, 5, 6. Okay. So We have seen these two spaces, right? Column space and null space. All right. So these two spaces talks about the matrix A. All right. More specifically, column vectors of A. Similarly, we have these two spaces, that is the row space and the left null space. So these two talk about A transpose. These two spaces talks about the matrix A transpose, or we can say row vectors of A. Okay. So what column space gives you about A, the same things row space gives you about the same matrix, but it's transpose version, A transpose. Same goes for null space and left null space. All right, so now we will see the visualization because we were considering this matrix from long, right? This matrix A 0 4 11 0 4 5 0 0 6. So we will see these the spaces for that matrix. So this is that matrix. All right. So sorry, these are the spaces for that matrix. So I have already explained you these two spaces. This gray that is the column space, and this blue that is the null space. So for now I will remove this from the visualization. All right. So what is this? This green plane is nothing but a row space, and I already told that row space is nothing but the column space of A transpose. So we will see that which all vectors passes to the column space. So I already took the transpose of this matrix, right? This is the transpose of the matrix. I just need to check what all independent linearly independent vectors are there. So all the linearly independent vectors will be in the column space of this matrix, in this A transpose matrix, right? And there is a way of calculating that, which is using the reduced echelon form. We will see that in the upcoming videos, but for now there is this tool which gives you the column space for a matrix, right? So either what you can do is you can take the matrix, take the original matrix A, do the transpose it A transpose, and then calculate the column matrix, sorry, column space vectors. Or you can directly, using this tool, you can directly calculate the uh, row space. Okay, so instead of transposing the matrix and then calculating the column space, this tool gives you direct calculation for the row space. So I just entered the matrix values, okay, and it gave me the row space. So these two vectors belong to the row space, so these two vectors will span the entire row space. So I will just simply plot these two vectors. So one more thing, these are the basis vector. Okay, these are the basis vector. Any scaled version, if this vector 101 belongs to the row space, then a scaled version of this, that is let us suppose 3 times 101, that is 303, also belong to the same vector subspace. All right, so I have plotted instead of plotting 101, I plotted 303. The reason being, I mean, if I plot 101, the vector will be very small. It will be hard to visualize. So that's why I plotted a scale version of it, 303. Similarly, we have on the second vector lying in this row space is 0, 1, minus 1. So I scaled it 3 times and it becomes 0, 3, minus 3. I plotted that as well. All right, so these are the three vectors you can see. Sorry, the two vectors. This is the first vector. This blue one is the second vector. So these two vectors belong to the row space. So we just need to find the plane passing through two vectors. So there's a way of I mean, you can like, it's a basic 11 12th maths, how to find a plane passing through two vectors. So if you calculate that, you will find this plane minus y minus x plus y plus z. So this plane, see this plane is passing through both these vectors, the blue vector and the red vector. These both vector, red and blue vector, are nothing but the vectors lying in the row space. They span the row space. This term is very important. They span the row space. All right. So this green plane is nothing but the row space for the same matrix which we talked earlier. All right. Similarly, we need to calculate the left null space. I already told you that left null space is nothing but the null space of A transpose. So in this tool, you can calculate the null space also. So instead of calculating the null space of A, I calculated the null space of A transpose. So this is A transpose. All right. This is A transpose. So this null space came to be 100 times t, where t is iteration. All right. So 100. So I can plot that vector as well. All right, so 100, so this is, here is that vector 100. So instead of plotting 100, I will plot a scaled version of it. So 300. Okay, so 300 will line the x-axis, right? Pretty simple. So the line passing through this vector is nothing but the left null space. That is, the entire axis is the left null space. So here is your final diagram. So we can see we have plotted three vectors here. The red vector and the blue vector, this blue vector, are lying in the row space, and the plane, they span the entire row space. So their span, the span of those two vectors lying in the row space is this entire green plane. Whereas this purple vector lying in the x-axis is lying in the left null space, and this entire x-axis, the entire red line passing through origin, is the left null space. So I think it's clear to you. All right. So if I just now plot all the spaces, so this is the null space and this is the uh, column space. All right. Just one thing, if you want to, in the upcoming lecture, I will prove this and show this. But yeah, always remember that the row space is perpendicular to the null space. So this green one is the row space. All right, this one is the row space. So this green one is the row space, and this blue one is the null space. So these two vector subspaces are perpendicular to each other, and you can see that. I mean, you can see this blue line is perpendicular to this plane. This blue line is perpendicular to this plane. So we can say that this blue line, which is nothing but the null space, is perpendicular to the row space, this green plane. All right, and similarly, the column space is also perpendicular to the left null space. The column space is also perpendicular to the left null space. So we have already seen this. The column space is nothing but the YZ plane. So what will be the left null space? It will be the x-axis. So we don't even need, if someone knows this property, so they don't even need to calculate the null space at all. Why? In this case, we know that the column space is the YZ plane. So the left null space need to be perpendicular to the column space. So the left null space, the only option left for left null space is nothing but a line perpendicular to the YZ plane passing through origin, and that line is nothing but x-axis. All right. So we can see that we have drawn all the visualization properly, because this property of perpendicular vector subspaces is following. All right. So yeah, these are the two subspaces, the row space and the left null space. All right. So next is a very important topic, is the dimension. What is dimension? What is dimension of a vector space? Dimension of a vector space. This is very important because a lot of questions are asked from linear algebra from this topic, difficult one also and tricky one also. So we will see this in detail. So first of all, the definition. The definition is pretty simple. It says that the dimension of a space is the dimension of a space is the number of vectors in every basis. In every basis. So if you haven't seen the video on basis, then I highly recommend you watching it because that is key to dimension. If you don't know what is basis, then you don't know what is dimension. But still, I will give you some refresher. So, for example, basis basically is nothing but it span the it basically span your vector space. All right. So, basis is basically the set of vectors, not too many, not too few. Set of vectors, not too many, not too few, that span the entire vector space is the basis for that vector space. So we can say that basis is nothing but set of vectors, not too many or and not too few. That is exact number of set of vectors that spans the entire vector space is the basis for that space, for that vector space. And basis set could be different. It's not necessary that for a vector space you have only one basis set. It could be different basis set also. So if you take this R2 vector space, then one basis set is this I hat and j hat. All right. Similarly, you can have one basis set as this some vector v and some vector w. This is the only condition, that these two should not be linearly dependent, and also these two should span the entire R2 vector space, and it is the case here. Okay. So the number of vectors in the basis is the dimension. So for example, for in case of R2, what is the dimension? The dimension of R2 is 2. Why? Because you take any basis set, you take any basis set. So for example, you take the basis set I hat, j hat. All right, maybe you take the basis set 1 comma 1 and 2 comma 3. These are linearly independent, right? So you take any basis set, all the basis set, the number of element in that basis set is always going to be 2, right? So you cannot take this basis set 1 comma 1 and 2 comma 2. Why? Because these two vectors doesn't span the entire R2, because 1 comma 1 and 2 comma 2 are linearly dependent. 1 comma 1 and 2 comma 2 is something like this. This is 1 comma 1 and this is 2 comma 2, right? So these are linearly independent, so their span is nothing but this line. Their span is a vector subspace in R2, but not the complete R2. So this set is not allowed. This set is not even a basis, not a basis set for R2 at all. So but these two are basis set of R2 and their dimension is 2. So you take any basis set for R2, the length of that basis set is going to be 2 only, and therefore the dimension of R2 is 2. Similarly, the dimension of R3 is 3. Why? Because you take any basis set, that basis set for R3 will always contain 3 vectors, because you need minimum 3 vectors to span the entire R3. All right. So from this, there is an important point. There is an important point uh, is that if V1, V2 up to Vm and W1 up to Wn are both basis for the same vector space, then remember that M will be equal to N. Because if they both are the basis set for the same vector space, then they need to be equal in length. Basically the number of elements in both the basis set needs to be equal. That is what basis is, right? That is what basis is. So we will see few example of basis set. All right, we will see few example of basis set. So also I already told you that the concepts like independence, basis, dimension are not limited to column vectors. All right, because vector space could be of matrices, it could be of functions, and for in that case we call it matrix space, function space, and it could be of any other thing. So same goes for the dimension also. So a matrix space, which is nothing but a vector space of matrices, also has a dimension. All right. So for example, we have this matrix space. We have this matrix space M. This we already seen in the previous lecture. that this is the vector space M contains all 2 cross 2 matrices, right? Then what's its dimension? Then the dimension of this vector space M is 4. How? Because any matrix in M can be written as A, B, C, D because it's a 2 cross 2 matrix. And the basis set for M is what? It is these four matrices, right? 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1, right? So any matrix A in the vector space M is nothing but a linear combination of these four matrices. All right, it is nothing but a linear combination of these matrices. So this is nothing but the basis set for M. Therefore, the dimension for the vector space M is nothing but 4. Because what is the dimension of a vector space? It is the number of elements in its basis set, and here the number of elements is 4. So these are the basis matrix. These are these are not basis vectors, by the way. Why? Because this space is not of column vectors. This space is of matrices. So these are basis matrix. This is a basis matrix, not basis vector. Always remember, because this is a vector space of matrix, not a vector space of column vector. All right. So here, let us suppose we see few examples. Let us suppose we have the entire n cross n matrix. So the dimension of whole n by n matrix space, what it is? Tell me. It is n square, because for 2 by 2 it is what? 2 square, that is 4. Similarly for 3 by 3 it will be 9. Why? We need 9 basis matrix in the basis set, so that's why the dimension of whole n by n matrix is n square. So you can also think it as that an n by n matrix will contain n different values, right? So here it is a 2 by 2 matrix, so a b c d all could be different, so you have 4 different values. So therefore you need the dimension of the basis set is 4, because you need minimum 4 different values to fill this matrix A. Similarly, in case of an n cross n matrix, you have basically n different values, right? A up to like a1 up to an and so on, right? So the dimension of this whole space is nothing but n squared. Similarly, the dimension of subspace of upper triangular matrix is what it is. So we will see. So what is an upper triangular matrix? So let us suppose we have a 3 cross 3 upper triangular matrix. So we know that there are value a b c 0 d e 0 0 f. So these values are always 0. Only these values are there. Okay. So how many values are there in each diagonal? So here we have one value. Then in this b e we have two values. Then we have adf three values, and so on and so forth, right? So if it is an n cross n matrix, it will go up to n, and we know that sum of first n natural number is nothing but n plus 1 by 2. So the dimension of subspace of our matrix is nothing but, we can expand this become n square by 2 plus n by 2. So this is the dimension of the upper triangular matrices, subspace upper triangular matrix, n by 2. So we need these many. So for example, if you have the 2 by 2 upper triangular matrix, this will be a b 0 and let us suppose d. So what all matrix are there in the matrix basis set? It will be 1 0 0, right? The second one will be 0 1 0 0, right? And the third one will be 0 0 0 1. Okay, this particular basis matrix won't be there in this vector subspace. Why? Because it's an upper triangular matrix. It's an upper triangular matrix. So if it is an upper triangular matrix, you cannot have an element here at this location, that is lower left. All right. So if you found this video helpful, then do like and subscribe my channel and share with others. Till then, bye. Thank you.